Hi everyone, I am Geetha, Assistant Professor, Department of Mathematics, SNS College of Engineering. In this session, we are going to discuss about convolution theorem on Fourier transform. The convolution theorem is a fundamental principle in Fourier analysis that relates the convolution of two functions to the manipulation of their Fourier transforms. This powerful relationship has important application in signal processing, image manipulation, and many other areas of science and engineering. Introduction to Fourier transform. Frequency domain representation. The Fourier transform converts a function from the time domain to the frequency domain, revealing its underlying frequency components. Periodic signals. Fourier analysis is particularly useful for analyzing and manipulating periodic signals, which can be expressed as a sum of sine and cosine waves. Applications. The Fourier transform have widespread application in areas like signal processing, image analysis, and quantum mechanics. Definition of convolution. Convolution integral. Convolution is defined as the integral of the product of two functions after one is flipped and shifted. Inductive interpretation. Convolution can be interpreted as a process of overlapping and summing two functions similar to the meshing of gears. Statement of convolution theorem. The convolution theorem states that the Fourier transform of the convolution of two functions is equal to the product of their individual Fourier transform. Symbolic representation. Mathematically, the convolution theorem can be expressed as f of f star g, which is equal to f of t into f of g, where capital F denotes the Fourier transform. That means Fourier transform of convolution of two functions. F star g denote the convolution of two functions, which is equal to Fourier transform of product of their individual transforms. Proof of convolution theorem. Step by step proof. The proof of the convolution theorem involves manipulating the definition of the Fourier transform and convolution using various mathematical identities. Deeper understanding. Understanding the proof provides a deeper appreciation for the underlying mathematics and the power of the convolution theorem. Practical applications. The convolution theorem has a numerous practical application in the field like signal processing, image filtering, and system analysis. Examples of convolution theorem. Convolution of Gaussians. The convolution of two Gaussian functions results in the another Gaussian function with the width determined by the widths of the original functions. Convolution of step function. The convolution of a step function with another function results in a smoothed version of the original function with the degree of smoothing determined by the step function. Convolution of sinusoid. The convolution of two sinusoidal function results in a new sinusoidal function with the frequency determined by the frequencies of the original functions. Visual illustrations. Fourier transform converts a function from the time domain to frequency domain. Convolution overlaps and sums two functions to produce a new function. Multiplication. The convolution theorem relates convolution to multiplication in the frequency domain. Coming to the conclusion, it is a powerful relationship. The convolution theorem establishes a powerful relationship between convolution in the time domain and multiplication in the frequency domain. Practical application. This theorem has a numerous application in signal processing, image analysis, and other areas of science and engineering. Further exploration, understanding the mathematical foundations and proof of the convolution theorem can lead to deeper insight and more advanced applications. Thank you.